Great. Welcome, everyone. My name is Zachary Brumbach. I'm one of the GSIs for this class. I'm here today to talk about Exam 1 for 3710. So the format of this, I talked a little bit about it before I started recording. The questions can be as broad as you want or as specific as you want. You can talk at a very high level about what is resistance, or you can ask me to solve problem 3 on the practice exam that was posted today. Any span of any kind of question about anything you don't understand or would like to see or would like explained, that's what this is for. With that, what sorts of questions do we have coming into this exam? Yeah. So exam 1 content ends at 3.10, RC circuits. So the most complicated and culminating type of thing that you should be expected to do will be a full RC circuit with a switch, right? Because that then tells me you can solve a circuit using node, mesh, Thevenin, Norton equivalent and analysis. You know fundamentals about reactive elements like your capacitor and inductor. You know Ohm's law. You know equivalent resistance. And with all of that, you can solve that like RC circuit in the end. So if you're able to successfully do one of those problems, that's like the end point of the material there. So for what that looks like lecture-wise, that was the end of last week. So this week is just labs 2 and 3. So it's all the content before this week. Yeah, exactly. Yeah. So Thevenin equivalent is a very important concept. Okay, it's one of the things that I think is often taught poorly without a true like understanding of why we would want to do it in the first place. Okay, so just to talk about where we want to end is we want to end. Oh, Jesus Christ! Apologies, my iPad refused to turn on today, so I have to use PowerPoint, which I'm not used to using. No, go away. Okay. So the goal is to end up with something very easy to look at, like a voltage source and a resistor. Okay. The goal is to take any super complicated circuit. Say I have like a source. Oh, this thing is so weird to type right on. And I have all these crazy resistors connected in different ways. So I have something like this, and I ask, what happens if I'm looking from this point, from here to here, call it A to B? What does this look like simply, right? Because the only thing I'm actually going to see at those points is a voltage and some sort of load or resistance. So a more typical application of this is like if I plug in my phone to a charger, right? That charger can act as maybe a resistor that delivers power. Sure, whatever. Not the point. But what does it look when it sees inside my phone, right? So sees is you'll see something that looks like this, some simpler version of a circuit that kind of sums up all the complicated stuff happening in a way that is easier to analyze and to look at and understand. So whatever this kind of complicated first step is, we want to get it simple. All right. So this is our Thevenin equivalent. Okay. And we can also write this as a Norton equivalent. So this is just instead of a voltage source, we have a current source and a resistor in parallel. Okay. What is that? Radio. Okay. Okay. So this is my Norton, where this we call ISC and this we call RTH. Okay. Where this resist. This is that same RTH and different voltage source here. And the relation here is just by Ohm's law. So V Thevenin is equal to I R. Okay, so you can go back and forth between these however you like. Okay, for something like a switch problem, like we talked about, would be the end of the material. Say if instead of this complicated circuit down here, say I had a capacitor. Okay, this is a perfectly valid first order RC circuit. Okay, first order meaning I have one passive element, my capacitor, and the R and the RC coming from we only have resistors otherwise. To look at this like that kind of switch or just that first order RC, we would treat this as my A and B, and we would solve for this Thevenin equivalent, which we'll talk about in a second, to then end it in a way where now I can draw my resistor back to where it plugged in on that A and B, and then use that to do the analysis. So instead of setting up some super complicated equation here, we can get it back here, and we know how to solve that problem. It is the same formula every single time. Okay, yeah.
So basically, the goal is to simplify it as much as possible, and then you can add in that like n component that you're looking for, and then just solve that.
Yeah, that's exactly right. So instead of having all these different resistors and current source and a voltage source, what if I just, this is a complicated thing, but if I'm only looking from two wires, I'm only really going to see a source and a resistor, right? And whatever that equivalent resistance ends up being, we have to find. But yes, we call this component over here that we plug in our load. Okay, so loading is the thing that we have to do in terms of like electrical components. Like when you plug in anything RF, like your TV cables, for instance, like it's a little dated, but something like the thicker coaxial cables on your TV, that's a 50 ohm load. And that's where you expect when the TV is connected to get the best power transfer so that you have that 50 ohms and you know what everything else is going to behave as. It's kind of how we use these things in a more practical sense. To find this from a circuit, you can always follow the exact same steps. Okay. Step one is find RTH. Okay. This will always be the same, and the other two you can pick between. So to find RTH, what you have to do is find equivalent resistance, capital R, from A to B. All right. So in this case over here, if I'm looking at my A to B, I'm going to sum this whole thing up into one equivalent resistor. All right. And the note here is that my voltage source becomes an open, a short, and my current source becomes an open. So if I wanted to analyze this circuit here, I would redraw it as a short, just a wire where my voltage source was, resistor, 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 and where my current source is, we now have a broken wire. And now here we have A and we have B. All right, so from here we would find R equivalent from A to B. Bang, we found R Thevenin there, okay? The reason why in these types of problems when we have a capacitor, we like setting A and B on the side of the capacitor is because you cannot find equivalent resistance with respect to a capacitor, right? So that's why we have to separate the capacitor off and just cut it out of the circuit and say, what is this actually seeing? Okay. And when I say seeing, I mean electrically. What are my electrons looking at as they're trying to flow? The next step, we can pick between two. We can find V Thevenin or we can find I short circuit. Here, to find V Thevenin, it is an open between A and B. And then you find the voltage between A and B, which is equal to V Thevenin, okay? So in this circuit I've talked about before, if we go back to having my current and voltage source, okay? Now when I solve this, I'm looking for whatever this voltage is, okay, from here to here. All right, that's how you'd solve V Thevenin in this case. You're solving for that voltage there. Whether that be node analysis, mesh analysis, any kind of combination of those processes, you need to be able to end with finding that voltage there. Did you have a question? Okay, so that is to find V. If we wanted to find I short circuit instead, ISC, there's a lot of kind of parallels or like complements in this class. We've learned that like For instance, like capacitors and inductors, right? One is the time derivative of the voltage to get current. One is the time derivative of the exact opposite, right? Here, to find Thevenin, we found an open between A and B. Here, we're going to short between A and B. And then you find the current through that. So the I in that wire AB is equal to I short circuit. So going back to this case here, where I was looking for that voltage before, now I draw this as a short, or just a closed wire, and I'm looking for this current in this part here, okay? And that's how I find ISC in this case. And the reason we only need to find two is because of Ohm's law, okay? If we have two of them, we can find the third. R Thevenin, typically the easiest to find. The second one is preference, okay? All right, questions about this? Yeah.
Here, keep that big equivalent is electrically equivalent from the low resistance perspective. Like for example, the voltage, like is the voltage we volted it, like are you thinking parallel?
Right. So the way we can kind of think about this is fundamentally, what is a capacitor? Like, what is a capacitor composed of? Just two plates, separate, right? So in space, I have two things that are fully separate, okay, where both of those are metal. I have some electric field that is storing the energy between these, and that is what creates capacitance in the first place. Anything that's not plugged in right now is considered capacitive. This empty socket right here, from ground to one of the nodes, has some capacitance between each different plug there, just through air itself. Okay, there is some capacitance, some amount of electric field between two charge points. Okay, that is when anything is unplugged. You can think of it as an infinite capacitor, just charging on both ends. And it's not discharging because there's no way for electricity to get from one side to the other. It's just perfectly charging forever. Okay, so again, think of these as two totally separate things. Okay, just for the sake of like the equivalent of a Thevenin here. So when I then plug this into my complicated circuit, all right, whatever the hell we want to draw, I want to get close to what we had last time. Okay, and here's my plug in my wall, all right? When I plug in anything, we first think of that empty plug as a huge, huge capacitor, okay? So that capacitor at steady state, at DC, is two totally separate metal plates. There is no current flowing when we don't have any movement in my electrical current and voltage, all right? So before we do anything, it acts like a capacitor at steady state, which is an open, all right? So we have two things charging forever, and then as soon as we plug something in, we'll go from that perfect capacitor to the resistor equivalent that is my Apple Pencil, okay? Say my Apple Pencil represents a 80 ohm load, okay? And when I plug this in, I'm going to get some current flowing into it, which is then depositing energy in the battery and thus charging my pencil. But what kind of voltage and stuff we're expecting to see as soon as we plug it in is derived from the idea that this is just endlessly open before we do anything. Okay, does that kind of make sense? You can say no. Okay, so what it's seeing is like at time zero, before I've plugged anything in, when I just have 2 points A and B, what is my voltage going to be at 2 points? And how well is my current going to flow in? Okay, so what my potential energy is at these points is defined by a voltage source. Okay, I have some potential that I'm plugging into that I have no idea what it is. I don't have current flowing yet, so this is why and people typically prefer the Thevenin equivalent to the Norton. So we have some voltage first, some setting of potential energy, and we have how easy it's going to be for whatever I plug in to flow energy just through the system itself, through the wall, through the power grid, through whatever this is coming from. Okay, there's some load here because it's not ever truly nothing, right? So as soon as we plug something in, say I have something that is really resistive, right? Say I have like 1 mega ohm I'm plugging in, okay? And my wall is acting like a 1 ohm resistor in there, a lot of very low loss. I'm going to have a massive voltage drop across this after I plug it in, right? And that's because my wall is not super resistive. There's not a lot of like kind of setup there. But maybe I'm plugging into something that has more of a load. Now, instead of, say, this is 10 volts, instead of seeing 5 volts when I plug this in, or instead of seeing 10 volts when this one was 1 ohm, now I'm seeing 5 volts here. So that's dependent on whatever the rest of everything that I'm going to be plugging into is before I even do anything else. Okay? Does that make sense? Mhm. So when we go back to like this case, when I'm solving for whatever this drop is across this, okay, I'm basically solving for what happens in steady state of that capacitor. So whatever my initial conditions are before I plug A and B into a resistor, into a phone, into an antenna, into an Apple Pencil. So it's whatever the potential at those 2 points are going to be. Is my V Thevenin is this? This one, that was supposed to be an arrow. That one there. How easy it flows as soon as I plug it in is dictated by whatever my internal load, my Thevenin resistance. So these two things define how well things flow after I plug something in, or the equivalent that I'm looking at from points A and B. Does that kind of make sense? We can talk about it more maybe after as well. So it'll be on the scope of like solving problems and what you're needed for this class, but there's a lot of interesting science there that goes beyond what I have time to explain in even a couple of hours. So yeah, other questions? Sure. Let's go for it. Um, Someone give me a number between 5 and 10. 6. I have 6 resistors. Someone give me a number between 1 and 3. 2. We're gonna have 2 sources. So say we'll have. Now let me make my life a little easier. I have a voltage source here, and this will connect down here. I'll connect that there. Say I have. Oh, I don't know. Another voltage source here. Ah, go away. 1, 2, 3, 4, 5. Let's call it 6. Here we have A, and here we have B. All right. Any circuit I draw should be able to be solved in some sort of Thevenin or Norton equivalent. Yeah. Mhm. Yeah. So Thevenin equivalent is just simplifying up a lot. So say maybe here is actually a super complicated second circuit with current sources and resistors, and maybe there's a capacitor and an inductor, and it goes crazy over here. I just have to draw that line, and then I can do the Thevenin equivalent for whatever's on the other side. So if it's not asking you explicitly and telling you where to do it, you can choose to do that. For instance, in this circuit, I could actually draw, say, call this A tilde and call this B tilde, and make this problem maybe easier for myself and solve for the Thevenin equivalent of this, or the Norton equivalent of that. And then I plug this into where my A tilde and B tilde are, and then I solve it again in whichever order I want. It's just taking anything and making it simpler. Okay. Uh, okay. So step 1, find RTH. Well, that's going to be really hard without values here. Someone give me a first voltage. I'll get your question 1 second. Just any number. 5 volts. Someone give me a second voltage. 12 volts. Now I need resistors. I want them all in kilo ohms. So give me this top left resistor. 3 kilo ohms. Next one. 9 kilo ohms. Oh, 9 kilo ohms. Next. 7 kilo ohms. Next. 5 kilo ohms. Next one. We got 2 more. We'll do 2 and we'll do 2 for the both of them. Okay. All right. So to find our Thevenin, step 1 is zero out all of my sources. So something that is 0 volts is a wire. Something that is 0 amps is an open. So voltage sources are shorts, current sources are open. So I'm going to redraw this now with my sources zeroed out. So I have 3 kilo ohms, 9 kilo ohms. This is a short. Oh my God. This is 7. This is 5. This is 2. And this one is also 2. All right. What was your question?
So if you had a capacitor,
Mm-hmm.
like A and B, and that's what we're looking for.
Yep.
But let's say the capacitor has like another side of the circuit and it's like super like complex, similar to the right left side.
Mm-hmm.
Would you like we wouldn't be asked to like solve like capacitance or something like that or the charge based on like you couldn't isolate one side. You'd have to isolate both sides and then do them together.
So actually, say I have some other super complicated thing. Maybe draw this a little simpler. So you're saying if I have something that looks like this, okay? Like this, right? And now I have my capacitor and I call these A and B. Well, if I call this A and B, that's the same thing as if I drew these out and I called it A and B. So we just essentially unplug the capacitor and treat it with both sides at the same time. Because how I draw a schematic is never unique. There's an infinite number of ways to do it, right? With components on like a PCB, for instance, a PCB is just a bunch of wires internally to connect components. I could reorganize it however I want it. It's just a spaghetti of metal wire. So whatever order it is, the wires don't matter. How these things touch matters. So here, if I'm looking at this, I could maybe redraw this as here, that same set of resistors on the left. And then I have resistor and resistor. And then I have current source. And then I have my capacitor. These are the exact same circuit, drawn in separate ways. So you just have to basically reorder it if it's easier for you to look at to just make that A and B. So, yeah, cool. All right, back to this one. Finding the equivalent resistance here. So before I even start looking at this, there's a little thing that I want to note. There's this path here, which is a wire in parallel with 2 resistors, all right? One way that you can kind of look at equivalent resistance generally is by highlighting your nodes first. And by highlighting your nodes, a node is if you were to take the Microsoft Paint tool and you were to drop it on a wire, how much of it is going to spread. It doesn't spread through components. So for instance, if I plopped it right here, I would draw this loop. It goes there and then there. So all of that is one node. All of that is one wire. Because a wire only stops when there's a component on it. When I'm going through a resistor. The actual line doesn't mean anything. It just means how I'm connecting. Okay. So all of this, say, would be like node capital B. Or let me change letters. We'll call this maybe C. All right. So the big thing that I want to note here is I have these 2 resistors that are connecting to the same node on both sides. So if I have a wire on both sides of a resistor, how much current am I going to get? If my potential is the exact same on both sides, if the height is the same on both sides, is anything going to want to flow down a slide like a resistor? No. So we're not going to get any current. These things don't matter. I can redraw this. Just like this. Oh my God. This is A, and this is B. This is 2 kiloohms. This is 2 kiloohms. This is 5 kiloohms, and this is 7 kiloohms. Okay, so these two get crossed out. Okay, from here, now I see 3 resistors in parallel because they share both nodes on either side of them, the terminals. So this now becomes the little R equivalent here. Does anyone have a calculator on them? My TI-84 broke. Does anyone have like a TI-84? Yeah, can I borrow that? So if I were to look at this, it's 1 over 7 plus 1 over 5 plus 1 over 2, which if we give that an inverse, that gives me 1.186 kiloohms. 1.19 in series with my 2 kiloohm. This is A and B. And now you can clearly tell that our Thevenin is just 3.19 kiloohms. That's the one. Okay. Any questions about that process? Yeah. Not necessarily. And there's no right way to do it either. It is purely like what you see and what's easiest to combine. Because we're not going to end up back solving for node voltages or mesh currents here. So all that matters is, hey, I see 2 resistors in series, let me combine them. Or hey, I see 3 resistors in parallel, let me combine them. In what order you do that, just combine, redraw, combine, redraw, combine, redraw, until you're eventually left with something like we have in the bottom right here, which very clearly just becomes 1 resistor because they're in series, okay? So it's whatever order, just keep simplifying with your just 2 rules of combining series and combining parallel. There will not be a case where you'll have to solve anything that doesn't follow the rules of series and parallel. Yeah. Oh, sorry. Did you have a question? It's fine if not. You're just pointing, but yeah. So what I combine here is in this first one. So I'm looking in this circuit. This 3 kiloohm and 9 kiloohm are in parallel with a wire. So if I were to solve this, it'd be 1 over 3 plus 1 over 9 plus 1 over 0, right? Which blows up my calculator. Math is very unhappy with that. You can also think of this as if I have a way to just perfectly slide down this circuit, there's no reason I'm going to take a complicated path through a resistor, right? There's no reason I'm going to go through traffic with these resistors if I have a perfectly open highway over here or over here properly when we zero out that voltage source. So that's why these two go away, okay? After they've gone away, I redraw my circuit where I have my 2 kiloohm, my 7 kiloohm, my 5 kiloohm here. And now using my rules of series resistors have a node, a unique node that nothing else touches, and then the other resistor. So that middle node can never touch anything else. Or parallel, where any resistors share both ends, so both nodes on either side. So if I'm looking at the nodes of this circuit, I have this one here that all connects to B, this middle one here, and this one A over here. And these 3 resistors all combine to be in parallel because this node and this node are both ends of all of these resistors. Okay, so this is 1/7 plus 1/5 plus 1/2, and take the inverse of it because that's how we do equivalent resistance. Okay. From there, the equivalent resistance of these 3 is 1.19K. Can someone tell me, just as a sanity check, why that number makes sense? Right. Exactly, right? It's smaller than my smallest resistor in parallel here. If I have multiple paths, the combined ease of those paths will always be lower than any one that I started with. Okay. So my lowest one starting here was 2, and then we ended with something less than 2. That makes sense. The opposite is true for series. Here I'm starting with 2 kilo ohms and 1.19 kilo ohms, which combines to give me something great. Okay. Simple sanity check to make sure you didn't royally mess up your math. Okay. Other questions? Okay. So just for completeness on this one, let's solve for Thevenin, so VTH. Now we're looking from the voltage from A to B. So in this circuit up here, I'm going to erase these lines for right now in the capacitor. One trick that's very, 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 very important that you need to understand to be able to solve these types of problems, because it's super common and you're going to see it throughout the rest of this class. When we're solving for voltage across A and B, okay, is A and B for Thevenin an open or a short? For Thevenin, do we consider A and B an open or a short? An open or a short? Yeah, right. So if we have an open on both ends, how much current is flowing out of both of them? 0, right? I have a dead end. No electrons want to go that way. So if I have 0 amps going this way, then how much voltage drop do I have across this resistor? Across this one here. How many volts am I losing if using Ohm's law, V equals IR, I is 0? Also 0 volts, right? So if I ever see this little floating type of resistor here that isn't connected to anything but A or B, I can actually redraw it here and consider this A, only for solving for voltage here. Because if I have plus and minus 0 volts across this, my voltage here is the same as my voltage here. Okay, so we essentially just ignore this one in full. All right. Any questions on that? Okay. So now when we're solving for Thevenin, I'm going to redraw my circuit. And here we have now A, and here we have B. All right. Step 1, I have actually made a flaw myself. Something that you cannot fundamentally do with circuits is operate without a ground. Voltage doesn't make sense without a point of reference. Okay. The same way potential energy in kinetics doesn't make sense if we don't have a height. Height has to be with respect to something else. Voltage is that parallel. We have to be able to compare volts to some reference. It's usually named as 0 volts, and if it's not drawn explicitly, I would suggest you draw it on your diagram. Okay. So I have a ground, I have my sources, I have my resistors. I'm solving for the voltage from A to B. Okay. So what are some methods that I could use to solve for that voltage? There's only, I think, 2 big ones we've talked about so far. Yeah. Mesh analysis and node analysis are the big 2. Okay. We can also use superposition, which is separating these 2 sources out and then using mesh or node analysis to then figure out what I'm looking at here. So for this one, I'm going to use node analysis because I'm looking for voltage. So node analysis is usually for voltage. Mesh analysis is usually for currents. Okay. So if I'm looking at this, step 1 in my mesh analysis. Step 1, name your nodes. Okay. So I'm going to name this node down here B, this node up here A, this middle one C, and this one over here, D. All right? So I have 4 nodes. That's great. I usually like to draw a little table for myself. VA equals VB equals VC equals and VD equals. Excuse me. Where our eventual goal is to find the voltage from here to here. So VA minus VB. Okay. The easiest one to know here, right off the bat, is node B. Node B is 0 volts. Okay. We know that because we've set that as our ground. Cool. All right. The next easiest ones are C and D because we have voltage sources. So they tell us going from whatever is on the bottom to whatever is on top. I automatically know what the voltage is going to be there because I literally have a battery telling you how much voltage I'm going to have there. So the V at D, the voltage at D is going to be 5 volts, and the voltage at C is going to be 12 volts. Okay. All right. From here, we only have one node left, right? So here you could continue to use your node analysis, which I will do, but let's get this to be 7 kiloohms, 5, and 2. And the other important thing here is list plus and minus for your components, okay? Okay, plus, minus, plus, minus, plus, minus. Okay, why is that important? Well, we make some assumptions when we're drawing these things, and one of those is that current flows in a direction, okay? Current will flow from positive to negative. So it's important for us to say which way a voltage drop in a current is flowing, okay? So if we have this here, and this one over here, if I get a voltage drop on one of these that's, for instance, negative 3 volts, that just tells me that I've got it backwards, okay? So going from the ground to here, if I have negative 10 joules of potential energy, that is you learning that I'm actually upside down and the problem isn't framed well, right? That's just kind of a point of reference. We need to be able to tell which way things are flowing. Likewise, if we get a negative current at any point, don't freak out, that's okay. A negative current just means you drew the arrow in the wrong direction. It just means the direction's wrong, okay? Negative 3 amps going this way is positive 3 amps going this way. It's the exact same thing, different label, okay? So solving for VA here, there's 2 ways to do it, and I'll do it both ways. It's purely whichever one makes the most sense to you quickly. The first one is with mesh analysis. So this is using KCL, which is the sum of I in is equal to the sum of I out. Okay, so we're going to use KCL to be able to solve this in a way that is quick. So at this node A, okay, coming in, I have this voltage across this 7 kiloohm resistor. Okay, so if we have V equals IR, we have I equals V over R. And voltage is always relative, so it's dropped from one to the other. So my voltage across my 7 kiloohm resistor there is going to be VC minus VA over 7 kiloohms. That's the only current I have pointing into my node A is equal to, and now I have both of these currents flowing out. So for the 5 kiloohm, I have VA minus VB over 5K plus VA minus VB over 2K. All right. Well, knowing that VC is 12 and VB is 0, I can automatically get this to be 12 minus VA over 7 kiloohms is equal to whatever VA is over 5 kiloohms plus whatever VA is over 2 kiloohms. All right? So I can then get this to be 12 over 7 kiloohms is equal to VA 1 over 7K plus 1 over 5K plus 1 over 2K. So this is just solving that equation that we've set up here. right, and if I solve this out, over 7,000, 1 over 7,000 plus 1 over 5,000 plus 1 over 2,000. This gives me 2.03 volts. Okay, that's way one. Cool. Method two would be if I'm looking at this block surrounding VA, I see that I have a 5 kilo ohm and a 2 kilo ohm resistor in parallel. So I would just go ahead and combine it because it doesn't really, we're not looking for currents there. So it doesn't particularly matter how, where, it doesn't matter that we combine them. Like we're not losing information. We would be losing how much current is going between each of them, but the voltage across them is the same, which is what we care about in this instance. Oh, come on. So this is the same thing as me saying I have some point, which I've assigned already to be 12 volts, going through my first resistor, which is 7 kilo ohms, and now into my equivalent resistor, ending with a ground. That is 1.43 kilo ohms. What can you tell me about this setup here? What does this look like? There's two types of circuits that we've explicitly learned the name, three types of circuits we've explicitly learned the name of. What is the type of circuit when we have a known voltage and then two resistors in series, or some amount of resistors in series? What do we call that? Yeah. Yeah, a voltage divider. Exactly. So I'm looking for my voltage here, and that voltage is 1.43 over my equivalent resistance, 8.43 times 12. 1.43 over 8.43 times 12. And that, thankfully, gives me 2.0, it's 36, but that's just a rounding error, volts. Okay? Two methods gave me the same voltage. Both will be right. Okay? It's whatever you see that makes your life easy. The whole point of showing you a billion ways to solve these circuits is so not all of them will make sense, but some of them will more than others. And then you can choose to follow rules that you think are easier. Okay? For me, I think node analysis is really easy for me. That makes a lot of sense. For some of my other friends in electrical engineering, they think that mesh analysis is the shit and they do it day and night like it's nothing. That gives me a headache. But pure preference. Same rules, same laws are being applied, so they can't be wrong. Yeah.
There ever be like a problem that we'd be given where you would explicitly have to use one over the other, or that we have the option?
I don't believe you should be given any case where it tells you explicitly how to do it. There are like for the sake of like an exam, right? We want to know that you know how to do both, just from a basic level. So yes, you will need to solve for a mesh current, or you will need to find a node voltage, generally speaking. But in actual application, when you get to something like senior design, or you're solving this for a homework problem, it does not matter at all. Okay, you should know how to do both, but you can secretly do one and then actually find the other, right? Because if I was actually doing like mesh analysis here, right? I know my voltage across this, so I know my current through this, and this current is the same thing as this current. So it's just knowing how to kind of trick the system a little bit. Okay. All right. Any questions about this? This is a full, complicated, absolutely generic Thevenin equivalent problem. This is as tough as these get because I made it up and there was no premise for simplicity or things combining easily off the get-go. Yeah.
This might be a little bit more broad, but
Sure.
in terms of combining concepts like this problem,
Mhm.
uses like Thevenin, but it also combines like mesh analysis, node analysis, and then it also combines like KCL. What of like, what is the maximum amount of concepts that you can like cram into one problem? Or is it more separated based on problem?
Yeah, so this problem could get more complicated because if I say I have a capacitor at the end of it, I could then ask you, what is the voltage across the capacitor at t equals 4 seconds? Which then you just solve for your time constant, you plug into the first order ODE solution that's generic for those. But it can only get a little bit more complicated as we've learned so far. With the switch problems, it is not more complicated than this. It's just a little bit of like a nuance off the get-go. You have to think about what are my initial conditions and how do they switch. So that's really the only thing to consider there. So yeah. Monday. Yeah, all day. So 12 a.m. to 11:59 p.m. I think it is properly midnight to midnight, but don't push that. Yeah. It would not because we would be starting from like steady state. So if I had a capacitor here, what I actually care about is like looking like a first order RC circuit because like all of this can just be combined from steady state of what my capacitor is going to react to. So all of that to say, like if I have a capacitor here, I did a whole lot of work just to then take the next slide and just redraw this as, what was it, 2.03 volts with it's like 3.19 kilo ohms, and now into my capacitor, okay, where these points were A and B. So it's just to say that instead of all of that complicated stuff and trying to solve for a time constant in a much more convoluted way, make your life easy. Only resistors will always create voltage drops versus like capacitors and inductors are reactive. So they change as a function of time, right? Resistors will not do that. Okay. As soon as my sources are on, there's no buildup for a resistor. It's just flowing 3 milliamps right off the get go. There's no like bump like there is with a capacitor, right? So that's the difference. Okay. Also, just for clarity on this one, the Thevenin voltage was that VA minus VB. So VA minus VB is equal to V Thevenin. So VA was 2.03 and VB was obviously 0. So VTH is equal to 2.03 volts. Just for completeness on that. All right. Other problems? Yeah.
Yeah, could you kind of like broadly explain like RC circuits?
Sure. Yes, RC circuits. So the whole like middle chunk of this class is going to be AC analysis. Okay. But how many of you are mechanical engineers? How many of you are aerospace? Okay. How many of you, what else do we have that takes this class? BMEs. I think, do MSCs have to take this class? Yeah, there we go. um, who else? What else am I missing there? Am I missing someone? What was it? Nuclear. I'm so sorry. I actually do a lot between material and nuclear engineering. But when some of the actual applications of this and why you would actually care about an RC circuit in the first place, is that you can model real things with this. Okay, a first order ODE ordinary diffie is the same everywhere. Okay, a second order is the same everywhere. And actually, when y'all take things like I forget if y'all get into it in like deformable bodies or if it's vibrations, I know does circuit equivalents, but you take mechanical systems and you compare them to an electrical because there's such a clearer analysis of how an electrical system behaves. So if I'm driving my car down North Side and I hit the curb and I bounce up, right? That's the same thing as an RC circuit. So you can model it. That's why you actually should care to know these things because that'll bounce and it'll have some sort of taper off as a function of time. For a first order properly, we're just charging up. So maybe that's like the little extender poles in like the back of like a gate of a car, how they like go fast and then slow down. That's kind of what a first order RC would look like. We'll get to second order in time, but That's why we care in general. To solve them, this is me plugging in anything. How does it immediately behave? How does that voltage spike up? How does it change? How long does it take to charge? That's broadly what an RC circuit is investigating and talking about. Does that answer your question? Cool. All right. Anything else? Yeah.
Um, we have to like incorporate the heaviside function, like running integrals, actual circuit itself. Was that more of just like additional step where we fucking
So the heaviside function is to model me hitting that curve. That's to be that immediate DC jump. Okay. So that's just kind of, we'll talk about that a little bit more in. So, um, you'll have to do those types of integrals if it's written explicitly, like here is the current across a capacitor. Here is I versus time, find voltage, which is just the derivative. But um, yeah, you won't have to do any like integration for this exam. If you guys are really struggling and banging your head against a wall and you have forgotten all differential equation, immediate solver, whatever, and you don't have your notes in front of you, you can solve the first order like RC, something that looks like this. If we treat this as like a mesh analysis here, you will get a first order differential equation. And if you were to use the things you've learned in things like differential equations, you'll get that formula back out. It'll spit itself back out at you perfectly. Okay. So you can choose to integrate or however you solve that. You can do that, but it'll be the same equation every time. Or first order RC. That's the whole appeal. That's the appeal of doing Thevenin and Norton equivalent. Thevenin in particular, because it gets us to a form where the differential equation is super easy to solve and has an established form. Okay. Yeah. Mhm. Yes. Yeah. One capacitor or technically one inductor, but you should expect one capacitor. Yes. Um. uh, Technically, it depends. Technically, you would call that second order, but you can model it as a first order if they are perfectly in parallel or series. But if they're anywhere separated beyond that, it becomes a true second order, if that kind of makes sense. Second order phenomena are much more interesting because, like, as you guys have seen, like lab two, right? You get that response that just kind of like generally charges to a point and like gets close but doesn't exceed. That's because all a capacitor is doing is storing energy in its electric field. Okay. But when we get to the second order and we have something like a capacitor and an inductor, the capacitor and inductor take turns storing energy. The capacitor in its electric field and the inductor in its magnetic field. And you go back and forth between two things storing energy, and that's how you get something like a sine wave. How you get a kind of response that's much more interesting than just like, right? Interesting, but yeah. Any other questions? Yes. I talked to Dr. West earlier today about this. I didn't actually realize that there weren't any posted, and I apologize for that. So there should be a practice exam posted now, and I believe the ones from previous exams will be posted with answers as well. There are a bunch of ones from like your homeworks and stuff. Your graduate student instructor should have worksheets, which should be good, like references for these types of problems. Should. Yeah.
um, two questions in
Mhm.
general. What level of difficulty would you compare the test to, like the homework,
Mhm.
the class worksheets? And then second, how long do you expect for us to take the exam? Like I know it's up to 2 hours, but
I usually reference the exams that I take and deliver to my students on a factor of if whatever amount of time I can solve it, I expect about 3 to 5 times the amount of time for a student to take it. So I looked at the exam earlier and it took me 15 minutes. So I would expect it to take you close to an hour. Okay. If you're sitting there diligently working and you know what you're doing. If you have to look back through your notes, it's going to take a little more time. I mean, yes, that's a fast time, but I do teach this class. So I hope it's a fast time, right? Um, the worksheets from my class, at least in particular, will be at the level of the exam or more difficult, just because that's how I like to write my worksheets. Because I don't like my philosophy is handing you those resources that you can use later and then using some amount of class time, but it's not the most important use of class time to me. So everyone who has their different instructors will have different worksheets, and whatever that looks like for you is whatever that looks like for you. The content will all be the same. The lecture videos are all the same. The practice exam and everything else will all be the same for everybody. You will all have access to those things. Okay. Does that answer your question? Okay. The hardest one that you should discard, whatever. The like upper limit. Let me see if I can find. No, I'm still in student view. Leave student view. The one that I kind of use is of like you can sit down and solve it. You really know what you're doing. I forget where it is in the EX page, but for where is that the big worksheet for? Oh no, that's probably not it. Worksheet no, it must have been 3 then. Apologies. Yeah. Did I not upload it? No, I apologize. I guess I haven't uploaded it, but oh no, there it is. Worksheet 6. Something that looks like this. Okay, your first order RC, where it says like find the voltage at t to the left, or just before time 0, find the voltage at t goes to infinity, find your constant, your time constant, and then find the voltage at some specified time. This is about as complicated as it's going to get. Yeah.
So the time.
Yep.
And then figure out like, okay, based on, you draw like a specific
Mhm.
diagram each time and then solve them like respect.
Exactly. So there's only 2 times you actually care about, 0 and infinity. And those are just your 2 steady states. That's really what you care about. So like, yeah. There should be a problem like this on one of the previous exams. I'm not sure where it is, so I'm just pulling this up for right now. So on the EX page, are there any practice exam? I think that got posted like. Okay. Okay. So I'll just show this here. This recording we posted to my YouTube and everything, or you can take a picture for now, at least. Um, but this is from a previous exam. That's where I'm pulling it from. So you should have access when everything gets posted when Dr. West does that soon. But just to like step through these steps real quick, this is as complicated as what we've already done, what I've already talked about here. So when they ask to find the voltage at T0 from the left, this is finding your initial condition, V of T0, okay? That's just the one extra step. So finding your voltage across this, which is actually V Thevenin, at T0, so that's before the switch happens. At T equals infinity, we close this and we find our new V Thevenin, so my new voltage across this. And then now we have my initial voltage and my V Thevenin. For tau of C1, my time constant is just R times C, and that R is R Thevenin. So this problem is really just asking you to find R Thevenin. And part D is just asking you to plug into the time domain formula, which is right here. It's just this V Thevenin plus initial condition minus V Thevenin, e to the minus t over tau. Okay. And you can kind of just look at this and intuitively know what it means by kind of scaling t. If t is 0, we have e to the 0, which is 1, right? And if we have v Thevenin minus v Thevenin plus initial condition at time 0, we'll have our initial condition. That makes sense. As t goes to infinity, right, this will keep getting smaller, this exponent, okay? So this whole side here will go to 0, okay? So as t goes to 0, this is a negative in front of it, negative infinity, e to the minus infinity is 0. This whole right part crosses out. As we go to t equals infinity, we get v Thevenin in there. Okay, that's just how we're solving this. That's kind of what this equation actually means and why we're asking for those limits of 0 and infinity in the first place. Okay. Other questions? Yeah.
Like the grading be graded for like
Yeah, for sure. for anything that's like true or false. But if it's something like solve this circuit and do whatever kind of analysis, and you get the final number wrong, yes, we'll go through it. We'll come through your work and give you all the partial credit we can. Yeah. Yeah, that's fine. Just don't use the internet. So I find it easier to use my iPad for things like this just because I don't have to go through the headache of trying to scan PDF. I know there's probably an easy way to do that in the camera now for like the iPhone, but I'll just use the iPad. Other questions?
It's pretty big. Why? So we
Mhm.
can like that,
Yeah.
like so. I guess for that kind of that's like what that.
So it's useful for if it's just another tool we can choose to use. Okay. So if I'm going back and PowerPoint is going to cooperate with me. Say I have a circuit that looks, oh, I don't know. I'll draw a simplistic case here first. Okay. All right. Say I have a circuit that looks like this. If I draw this as A and this as B, right off the get-go on the left, that's a Thevenin equivalent circuit, right? Okay. Where this is V and this is some capital R. I can redraw this circuit using and my Thevenin to Norton kind of conversion that we talked about. So it's a voltage source in series or a current source in parallel. So I can redraw this as now a current source, right, with that same A and B, where this is capital R, and from here, I equals V over R. So that's the current that current source is applying. And this is with those other resistors. This is a current divider. It's just an easier formula than trying to solve the first one. It's just kind of pure application of if you want to go back and forth and when you want to do that. So in this case, I could move it here, and then I could combine all three of these resistors for something really easy to find the voltage from A to B, or it's just another tool that kind of, as you see it, you can use it. You won't be stated to like, for this class, it won't be solve this circuit using only source equivalencies. That's not going to happen. So it's just kind of like a, hey, I know what that looks like, and I think it would help me right now. Yeah. Okay. Sure. Yeah. Yeah. Okay. Let me go. So this is, instead of using something like mesh and node analysis, we can skip that in full if we can just use like equivalent resistances. Okay. So if I have something that looks like this, okay, and you're asked to find this current, okay, we'll call it I4. And you're also asked to find this voltage, call this V 1, 2, 3, 4. So that's okay, VD. All right, if you're asked to find these two things. One of the ways we can do this is by combining resistors one step at a time. So eventually, I'll combine this first. I'll combine the things that I see that are easy. Oh, oh, like this. And this is still someone's got an air tag. And this middle one is still I4. Okay. So what I've done is I've collapsed these first two. Okay. So now the current here, this I new, this is I6 and I7. Okay. So this I new is different than each of these currents. Okay. For combining components, that current is not the same. It is some combination of those, but what that is, you'll kind of have to solve in any relation that makes sense there. So in this particular case, this is the sum of my previous 6 and 7. Okay. So if we keep collapsing this, we're going to put these two in series. Okay. Oh my God, I'm so sorry. yes, sorry. So if we have this resistor shaking, replacing this blob, okay. Now that I've combined those two resistors, this middle node is gone. Okay. So what I'm going to have to do is eventually, I'll keep going down and being able to solve this. I'll find what my voltage is from here to here. Okay. And that voltage will be the same as my voltage from here to here. Okay. Because this node and this node are the same, and this node and this node are the same. Okay. So this is all just going to say that as I continue to squash stuff down, I need to be able to work back up as well. Okay. Let me redraw this real quick. Actually, that's fine. So say I find this voltage from here to here to be 7 volts. Okay. That's cool. So how do I find VD knowing that full drop is 7 volts? Okay. So if I get way down to simplifying and I get it to something super easy, a voltage divider, I'll be able to solve for this voltage, which then that keeps breaking apart, and I keep having to use voltage divider laws or current divider laws to keep defining what that's going to be. Okay. So say I do know this voltage, okay? I'm now missing VD because that node got erased when I stepped here, right? So I know that from here to here I have 7 volts. And going in, I have some resistor and some second resistor. And this is VD. This we would use a voltage divider here. Okay, so all it is like as the most important thing if you're simplifying a circuit is keeping track of what is what. Name your nodes. Keep them straight, okay? If I'm looking at this first one, I need to name these just so I know what they are. What? A, B, C, D, E, all right? And as I continue to combine things, A, B, C, E. I need to note what I'm getting rid of as I'm combining resistors. Okay, so this node D goes away as I start to combine. Once I know, for instance, VC, oh, that's new. How did I even do that? No. So if I know VC and I know this resistor, or rather if I know VC and I know this equivalent resistor here, I can find VD by just using the rules of like a voltage divider there. Okay. All right, any other final questions before we end? Yeah. Yeah.
Like, I feel like there are some circuits where I try to use a lot of source transform.
Yeah.
Where there's not like there's no resistor in series with the voltage source, or like even if I turn it into Norton, it wouldn't be in parallel.
Yeah, that probably means you need to do some combining over here before changing your source back and forth. You absolutely could. So you're saying if like we had something like this and it wasn't as simple, So say it was something that looked maybe a little bit more like oh God, I don't know. Why aren't you erasing? Okay. So you're saying like if I have a Thevenin equivalent, okay, and this is connected to something that isn't directly in like series or parallel. So something more complicated looking. You're saying like if this connects here and it's not evident with source transformations, how do you proceed? Is that what you're asking? Okay. Um, the first thing I would think to do is combine stuff that is in series or parallel. So that would be like combining these two and combining these two. Okay. And then from there, this is actually unsolvable in terms of what we've done for this class. This has something called a delta Y transformation, which we don't go over, but that's not the point of what I'm trying to say is you need to try to simplify other stuff to see if it's easy from there. Yeah. Mhm.
that there are
Sure. Hmm. Yeah, they're complicated for sure, but um, usually what I would do is if I'm looking for an equivalent resistance, I would usually simulate it, to be frank. But to compute it schematically, right? Like, yes, you would keep following those, and then as you do a transformation, something is going to combine. As you do another one, something else is going to combine, and that's going to keep happening. Okay. So it's a tough place to be, and it should always get easier, but it just means you probably need to look elsewhere for a place to combine, not just where the source is and source transformations for that. Does that make sense? Okay. With that, good luck on your exam. I have my office hours, my final office hours before the exam tomorrow morning at 10 to 11 in Tech Square Research Building, 5:30. That's on the Canvas page. Um, yeah, good luck. I'm sure you all will do fine.